use the green hydrogen, and we use the carbon dioxide we captured, and we convert it to SAF. We call it electrolyzed SAF or ESAF. ESAF. So the full name is electrolyzed SAF. Okay. So again, I think I showed this picture many times. Even last year, I showed this picture to you guys. Like, we need these processes to make and develop and make this fuel going commercialized and make this fuel to the market. The first one, of course, is the laboratory development, right? So, what is the SF? So this is a HEPA stuff I used to develop, starting from the glyceride oil, okay, from cooking oil, from waste cooking oil, okay, from palm oil, something like that. But now, the new one is what I'm going to show you, which I have been doing these years, is the ESAF. So we have a carbon capture process, which we grabbed the CO2. You are producing CO2. Everybody is producing CO2 because there is a combustion system inside your body. So you are producing, so this CO2 is everywhere, but how do you get it? Get it from the company, get it from the factory, get it from the motorbike, get it from yours, like all the atmosphere, okay? How can you get it? So, and then we also need a green hydrogen because E is electrolyzed. So how to produce hydrogen from green hydrogen from the water or something, okay, use the green energy. And then we convert the CO2 to SF. And finally, if we have the leftover extra hydrogen, use the fuel cell to make the power generation. So this is the new development in for SF. And now, as far as I know, in Korea, they put 200 million NTD, dollars, 200 million, yes, for this kind of project. And this is the one. I'm also a co-PI, so I work with Hanyang University in Korea on this topic. Right? But this topic now is only supported by TSMC. TSMC now putting money on it. Okay, they want to have a green stuff. TSMC, Taiwan Semiconductor Company. So they want to put everything green. So the first one is a carbon capture. I got so many slides, but I will make it slow and make it easy, understandable. But I'm not going to finish it. Okay. So once the time is up, let me know. Okay. So the first one is the carbon capture. The carbon capture, we can capture 95%. In summary, we can capture, which means 100 kilogram, I can capture 95 kilogram of CO2. Okay. And was the absorption capacity 0.69 millimole per gram. And the CO2 I'm releasing out, when I capture, the purity is 97%. Okay. So that is, and the one we developed, the carbon capture system we developed, there are some specialities. Number one is it's designed based on the aerodynamic knowledge. Okay, so in terms of systems, it's more efficient and less energy consumption compared to other carbon capture systems. Number two is it runs at room temperature and low pressure, like 1 atmosphere. So it's low energy consumption. Number three is continuous. So it capture, release, capture, release, capture, release. So I can make a use of CO2 anytime, anywhere I want. Number four is the absorption is cheap and lifetime. So the whole process I can go for commercialization. And the last one is a systematic design. So easy to scale up for fit for purpose. Okay, so this is an experimental setup. This is a continuous process we designed. And this is like one doing the capturing CO2. And once you capture, you want to use that. So another tower, we call another chamber is called releasing the CO2. So one capture, one release, and then we switch. And one capture, then one switch, one capture. So it like take turns, keep taking turns. So it can continuously, I'm saying continuously capturing the CO2 and continuously feeding the CO2 to my SAF production system. All right, and this is the design, aerodynamic design. If we have a aerospace department professor here, this is like our wind tunnel. Okay, I designed this idea based on our wind tunnel idea. Okay, so I calculated chamber length, I calculated angle of diffuser, I calculated honeycomb porosity, I calculated mesh porosity as well. Okay, and we do the computational fluid dynamics design for design this chamber. Okay, we also study the absorbent. We look at the microscope and also the functional group of our absorbent. Okay, and the thing is, this absorbent is coming from very cheap active carbon. We use the nitrogen doping for active carbon. So it makes the efficient super increased, right? So this is a new design. And also we look at the temperature as well, okay? Temperature as well, because this is an isothermal reaction, so it's releasing the heat. So we look at the temperature and see if the temperature goes up, which means it starts absorbing the CO2, right? And then we calculate the performance based on these 5 equations, just like I said. What's the efficiency capturing the CO2? How much CO2 you're capturing, and what's the purity of CO2 you're capturing, and CO2 recovery and productivity. All right. We also study the process operations. We study the temperature. We study the pressure. We study the absorption flow rate, and do the process optimization. And the optimal process, like I say, we can absorb almost 95% of the absorption efficiency, was the purity of CO2, 97%. We can recover most likely 87%. Okay, was the absorption capacity about 1.9 millimole per gram. We also study if the feeding gas, because most of the gas coming out from the company or from the factory or from steel or petrochemical company are hot gas, very high temperature. So we also look at the high temperature feeding gas, okay, and we still can maintain the capture efficiency and purity. We also look at the water vapor addition, because we have the water vapor feeding in, okay, and then we'll see what's happening. And also we find a solution for recover the capture efficiency from the for the heating process. Okay, so that's the first step. Okay, second one, we try to convert the CO2 we captured continuously going to the SAF production process. Okay, so we make our own catalyst and we try to convert the CO2 to our SAF fuel, SAF fuel. Okay, and this is our system setup, and we use these equations to make sure, okay, the SAF we're making is correct. We also monitoring the exhaust gas. We monitor the temperature, okay, because this process is also an exothermal process, so we need to make sure the temperature going up to make sure the process is ongoing. We look at the hydrogen, or we look at the hydrogen concentration, because we want to make sure the hydrogen consumption is correct, okay? And if we have some leftover hydrogen, we can use the fuel cell, put in downstream to make the power generation. We also have watch the CO2 concentration, because we have to make sure the CO2 conversion is right, okay? And also we watch the CO concentration as well, because the CO concentration will tell us, okay, later on if I can use the fuel cell to make the power. Okay, and this is the hydrocarbon compositions of the produced stuff. Now, our I2N ratio probably you don't know, like the I2N ratio is the isomer to normal alkane ratio, which is a very important index for SAF. So now the I2N ratio is about 0.9, okay, but the most proper ratio is 1.